You're almost at the end of understanding the keyword spotting application. After this, you're going to actually deploy the keyword spotting model onto your embedded microcontroller. Here, I want to help you understand how to digest the vast amount of complexity that you might be feeling at this point. Now, that we stepped through many different functions, and we discussed about all the different topics that involved, around the code constructs. And we looked at a lot of code in the form of raw files. So if you're feeling overwhelmed, don't worry. There's a method to this madness, and I'm going to teach you how to think about this systematically. First and foremost, there's the whole notion of setting up the environment, and there's a set of hows that were involved there. When you go into setting up the ops and the interpreter, and that requires that you look at a couple of functions, usually in the setup portion of the code. Then we actually got into ingesting the data from the microphone, which is the pre-processing part of the application. And this can be a little complicated. And remember here, you have a device-specific portion, which is where you're dealing with the specifics of a particular microcontroller, for instance, and the way it interfaces with the I/O subsystem, specifically from the embedded sensor part. And then there is a non-device specific aspects where you are simply processing the raw data, converting the input buffer data of audio signals into the spectrogram. Keep that in mind because those two things are very different. And once you have that, you invoke the interpreter with the right data. So you're typically copying, the raw signal, and you have perfected it into the features and that you're giving over to the interpreter, and which then performs the inference. And then it generates, outputs, and the output is something that we can act on by looking at the actual output of the network to be recognized, as a word or not, and decide if you're going to actuate some sort of LEDs, into another subsystem. So most of the code is kind of largely sprinkled along these modules, and you could very well be the framework, for the way you need to think about digesting a large volume of code. That's lesson number one. Another thing around this is that there are many different components that we step through. Now, how do you kind of make sense of, what to change and what not to change? Let's say you want to make some sort of tweak to the application. You've got to think about, this is not thinking of the whole code is, it's going to be very overwhelming. So what you really have to do is recognize the fact that the end-to-end application is really broken up into 4 big building blocks. There's setup, there's the pre-processing, there's the inference, and then there's the post-processing. And you tend to repeat the cycle between pre-processing and post-processing over and over and over. So pay attention to the different parts that I have listed out as examples that fall underneath each one of these components. For example, in pre-processing, you have the KISS FFT, or that's where you would do the MFCC. Let's say if you want to enhance a spectrogram that you are actually generating, well, then you just need to focus on the pre-processing. And you don't need to really worry about the other pieces. But keep in mind, though, if you change the pre-processing step here before you call the network, then you've got to make sure your network has been trained accordingly in the earlier stages, like in the part 2 of the course. Keep that in mind. You simply can't change the pre-processing step and expect the network to perform better because the network has learned the features that the pre-processing is actually doing. So it's extremely important to keep in mind that if you were to go back, that you have to go back and retrain the network with a new set of pre-processing steps that you're doing. Something that is quite subtle actually, but very important. Similarly, if you want to improve the network's performance through optimization, well, then focus on the network part. And if you want to improve the confidence of the system, then focus on the post-processing side of things. You don't have to look at the whole code as one monolithic blocks, sprinkled across different files. There is structure, in the large amount of code that you're using. And if you want to modify something, identify what you want to modify and only focus on that part. And that's the key lesson over here. One of the reasons I have specifically broken down things into the setup, pre-processing, inference, and post-processing is because it's rather an important message from the end-to-end application and design perspective that I want to convey over to you. Now, remember, right at the beginning of this course, I said that we are going to do things a little different over here. And we're not just interested in the model capabilities and not just interested in coming up with the smallest neural network. We're actually interested in orchestrating the full flow and being able to design an end-to-end application so that it runs effectively. And on that note, know that the setup, pre-processing, and post-processing are just as important, if not in some sense, more important than the actual network model that we are doing our inferencing on. Why do I say that? Think about it from the execution latency perspective. You have to do setup once, and then after that, you have to do the pre-processing, inference, post-processing, all in real time while the device is actually running, trying to detect your keyword. What that means is that they actually all add to the latency. And this is just a pictorial representation of what the latencies might be. I'm not necessarily saying that pre-processing is always the most biggest chunk. Either way, the point I'm trying to convey here is that they have different amounts of overhead, and those overheads can be sometimes larger than the inference itself. So when you're trying to optimize your device for performance, keep that in mind. Similarly, from a memory standpoint, you need to keep this in mind. Pre-processing, post-processing, setup, they all consume that limited amount of memory that we have on our microcontroller. So we need to keep that in mind that as we try and optimize a system. And this is also the reason earlier I talked about the embedded system software stack, because the embedded OS and all those things actually eat up memory. So you need to be conscious about where you're going to tune the memory resource requirements if you need to do so. The bottom line is that both in terms of execution latency as well as in memory, there might be different overheads that are all coming from non-machine learning aspects. In other words, if I take inference out, there is some AI tax that is left behind, as I like to call it. And the AI tax is a pure overhead. So when we are designing applications to be efficient from an end-to-end perspective, as we need to do in keyword spotting to actually get it to work, well, then we need to also pay attention to how quickly we are able to do this processing. That's why, for instance, our version of FFT in the pre-processing stage is actually very simple. It's actually not the best FFT that you can run. It's actually called KISS, as it stands for Keep It Simple, Stupid. And that's literally what it stands for. But you understand the notion of keeping things simple, and that's what's important. So keep AI tax in mind, because that'll help you be a better TinyML engineer, because you will be able to understand what it really means to design an end-to-end application. Now, with all that said, you can now take the model and deploy it on your embedded system. And also later on, we'll be changing the model in response to a new data set. So a lot of exciting stuff is coming up. And so stay tuned for that and have fun deploying your code.